Next, we will analyze such an equation where 2 lambda equals R over L and omega 0 square equals 1 over LC. Its characteristic equation is lambda square plus 2 alpha lambda plus omega 0 square equals 0. Since it's an algebraic equation about lambda, its solution may have several different forms. First of all, if lambda square greater than omega 0 square, then we know the characteristic equation has two different real roots. That is, lambda 1, 2 equals minus alpha plus minus square root of alpha square minus omega 0 square. According to our previous study about the second-order linear ODEs with constant coefficients, we know that the general solution of the equation can be written as the form of UC equals A times e to the power of lambda 1t plus b times e to the power of lambda 2t. If lambda square equals omega 0 square, then the characteristic equation has two equal real roots, which can be written as lambda 1, 2 equals alpha. In this case, the general solution can be written as a form of UC equals A times e to the power of minus alpha t plus b times t times e to the power of minus alpha t. The third case is alpha square less than omega 0 square. We know that the equation has two conjugate complex roots, that is lambda 1, 2 equals to minus alpha plus minus j times square root omega 0 square minus alpha square. According to the previous discussion, we know that in this case, the general solution can be written as a form of UC equals k times e to the power of minus alpha t times sine omega dt plus theta, where omega d is defined as square root of omega 0 square minus alpha square. We will also give the definition and discussion about omega d later. The fourth is special, where alpha equals 0. In this case, the characteristic equation has two conjugate imaginary roots, that is lambda 1, 2 equals plus minus j omega 0. Similar to the previous discussion, we know that its general solution can be written as the form of UC equals k times sine omega 0 t plus theta. Here, A, B, K theta, K theta are all underdetermined coefficients of the general solutions. For the four cases, we define them as overdamping, critical damping, underdamping, and no damping. Here, the so-called damping is actually refers to the block effect due to the existence of resistance or loose term during the whole process of energy conversion of the dynamic circuit. Overdamping refers to the very big block effect. Underdamping is not so big, and the critical damping is between these two states. No damping has no block effect.